Hey guys, I'm here to show you guys how to do the sort of conversions into state space with multi-degree of freedom systems a bit more quickly or easily. I want to emphasize, excuse me, I want to emphasize yet again that this is specifically for linear or linearized multi-degree of freedom systems. Okay, if you don't have that, you'll have to go back to the hand calculations that we showed earlier, or you'll have to look into some other methods that maybe someone has found, whether in some kind of text or on the internet. But in any case, just remember that that's the restriction of everything that I'm about to show you guys. Okay, here we're working with the same system that we had in the previous video. I haven't shown the block and the pendulum and everything, but I have written out the equations yet again, as well as the conditions showing that, yes, I have linearized this equation about its equilibrium position, right, where x naught and theta naught are both 0, okay? You really should know some basic things about matrices and matrix multiplication and, some very basic terms in linear algebra if you're gonna dive into this video, or you can gain that information as we go along if you haven't gained that information before. It's not very complicated, it's not very detailed, but knowing it will benefit you and is necessary to get some kind of idea of what's going on. Alright. The information that I'll be showing you guys comes from a textbook, and I'll show it up here. You should be seeing it right now. I also have the name of it in the description, and this is where I got the information from. This book holds the whole derivation for what I'm about to show you. I'm not going to do the whole derivation. I'm only going to show some really basic things that you'll need to know, and that's going to be it. So if you want that information, you can look there, or you can look to another vibrations textbook or to the internet. But with all that being said, let's get started. So the important thing here is that, let's say we have some n degree of freedom system and we have n equations, right? It could be 2 equations, it could be 30 equations, whatever. The important thing is that if we have n equations of motion, we can break this down into a matrix equation, all right? And that equation will look like this. It'll have some matrix M times some vector Q double dot plus the sum of 2 matrices C and G times some vector Q dot plus the sum of 2 matrices K and H times some vector Q. Alright, and all this is equal to some vector F. Now I know this looks complicated, there are a whole lot of letters everywhere. Don't let it scare you away. Trust me when I say this is faster and simpler in a number of ways. Alright, so let me go through these guys. M is your mass matrix, alright? It's a matrix that holds the information about the masses in your system and how they relate to your equations. C is the damping matrix, which holds the information about the damping in the system. G is your gyroscopic matrix. K is your stiffness matrix. H is your circulatory matrix, okay? And F is your forcing vector, alright? The vector that holds all the relevant forces that are involved in your equations of motion. You're probably wondering what these Q's are all about. These Q's are just to represent the functions that you're solving for, alright? So for example, let's say I'm solving some 4 degree of freedom system that has X and Y and Z and theta, okay? These are the guys that I'm interested in finding out. Alright, then my vector Q would be X, Y, Z, and theta. I'm sorry if I'm not drawing these to look very pretty. My vector Q dot would thus be X dot, Y dot, Z dot, and theta dot. And from this, I'm sure you can guess what Q double dot would be. It's going to be X double dot, Y double dot, Z double dot, and theta double dot. So Q is really just a vector showing the functions that we're solving for. Q dot has those functions' derivatives with respect to time, and Q double dot has the second derivative of those functions with respect to time. Alright? So that's what each of these guys means. Okay? Now, what exactly do we do with these? Why are they so important? Why am I showing you guys a ton of random matrices and vectors and stuff? The reason why this stuff is so important is that we can get the derivative of our state vector pretty much directly from this information. Alright, there's an equation that says that the derivative of our state vector, S dot, is equal to some matrix A times the derivative of our state vector plus some matrix B times our forcing vector. Now, if you know your equations of motion, you should already know what your forcing vector is, but you're probably wondering where A and B are coming from. And A and B come from the matrices that you already have from your equations of motion. Alright? Specifically speaking, A is it's a 2n by 2n matrix. Okay? And it is composed of these components. In the bottom left, we have the negative of M inversed, of the mass matrix inversed, times the sum of K and H, our stiffness and circulatory matrices. In the bottom right, we have, again, the negative of M inversed, this time being multiplied by the sum of C and G. Running out of space here. Where again, C is our damping matrix and G is our gyroscopic matrix. In the top left is the zero matrix. And this zero matrix is an n by n matrix. And in the top right, we have the identity matrix, which is also an n by n matrix. Okay? You should know what these guys are by now. Again, if you don't, you can look that information up. But this is what A is. As you can see, it's not very complicated. Next up is B. What is matrix B? Right? B is a 2n by n matrix. And it's equal to the zero matrix, which is again an n by n matrix, up top, and then on the bottom we have the inverse of the mass matrix. And that's it. So B is a much simpler matrix to work with. Keep in mind, again, that n is the number of equations that you have. Alright? So just bear that in mind. And oftentimes, again, if you're working with these multi-degree of freedom systems, and it'll be the number of degrees of freedom that you have. The last thing is S, right? You should know your forcing vector from your equations of motion. You can get A and B from these equations, okay? And these equations really come from your equations of motion because the zero matrix and identity matrix are really easy to get. We know them because they have a specific definition. And the mass matrix and stiffness matrix and blah, 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 all these guys are also a part of our equations of motion, okay? So the last thing that we need to know is what is S? What is our vector of states? And I want to make sure that you guys know that it has a very specific definition, okay? So what you're used to seeing me doing is, you know, something like x, x dot, y, y dot, z, and z dot, all right? For this equation, you don't use this representation, okay? It will not work with this specific form of the equation, okay? Instead, you'll write it like this. X, y, z, and x dot, y dot, z dot, right? Or if you're using the notation that we had earlier, you can consider it as a vector holding q and then q dot. Okay? So that's what you need to keep in mind. You won't really have to worry about doing this by hand because you won't be doing this by hand. MATLAB's going to take care of it for you. But this is important so that when you pull results out of MATLAB, you'll know what each column in your state values represents, right? You don't want to mix it up with this representation because this is the representation that you'll be using, okay? So now we know what our vector of states is, S, okay? We know what B is, we know what A is, we know what F is, so we have all that we need. And all this information gives us the derivative of our state vector. And that's it. That's all we have to do. So we can plug that into MATLAB. Let's go ahead and work with our example that we had earlier so that we can use an actual physical example with MATLAB. Alright, so I'm going to write out these equations again. If m1 plus m2 times x double dot plus m2l theta double dot plus cx dot plus kx equaling f of t. And then the other equation is m2l x double dot plus m2 l squared theta double dot plus m2 g l theta. And all of that is set equal to 0. Alright, so these are our two equations, and you want to get this in the form of a matrix equation. Now, I'm not really going to walk you through how to do that, but if you see the matrix equation that I'm going to write, you should kind of be able to get an intuitive feel for what that looks like. Or you can look at other examples as well, okay? Again, the matrix equation in its very generalized form looks like this. Okay, we have that mass matrix there. We have the sum of these two matrices here. And then we have more summed matrices here. Get that Q vector in there, and maybe I'll fit F this time very slightly. Okay, we kind of made it in there. Okay, so in this example, there are no gyroscopic or circulatory terms, obviously. We only have our masses and dampers and springs. So I'm going to cross out these guys and just say that there's 0. More accurately, 0 matrices, but whatever, okay? And if I were to write these two equations in matrix form, they would look like this. Let me see if I can fit this in. In the top right, I have m1 plus m2, or that's the top left. In the bottom left, I have m2l. On the bottom right, I should have m2l squared times theta double, oh my gosh. Losing track of what I'm trying to say. m2l squared, and then on the top right, I should just have m2l, okay? This is my mass matrix. This is going to be multiplied by x double dot and theta double dot. And this represents my q double dot vector. Okay? I'm going to add to this the damping matrix, which is very easy to write. It's just this. Okay? It's going to be multiplied by x dot and theta dot. So this is my damping matrix. This is the equivalent of my q dot vector. Make sure it's clearly one dot. And then I have my stiffness matrix, which is going to have this k here, 0 here. Let me see if I can fit this. M2GL here, 0 here. Alright, and that's going to be multiplied by x and theta. And I cannot fit the forcing vector this time, sadly. I need to learn to conserve space. So all that is set equal to f of t and 0. Alright, and I'm going to point out that this is my forcing vector, this is my stiffness matrix, and this is my q vector. Alright, so if you aren't familiar with extracting, your equations into matrix equations, you'll notice that if I were to multiply through matrix multiplication, all these matrices and vectors and add them up as this equation tells me to do, then I'll end up exactly with these two individual equations of motion. Okay, that's the point of making a matrix equation. It's a matrix equation such that if you were to multiply and add all the terms appropriately, you would end up with the same equation that you had if you hadn't grouped them into matrices yet. Okay, that's really all there is to it. This is all that we need to start working with MATLAB. So I'm going to circle this guy. I really hope that the extraction into matrix part made sense, but if it didn't, you can always look at some examples online. I'm sure that they're out there. But with this, we can go ahead and leap into MATLAB. Hey guys, and welcome back to the MATLAB environment. Now this time I'm going to do things a little bit differently. Usually you see me, scrolling through two codes and then writing out the last one, which is most often the function handle method. But this time I decided that it might be best for me to write all the code beforehand and then kind of walk through what I did in them just to make more sense of things. It's not that complicated really, but with problems getting more complicated like this, where we're involving matrices and such, it's getting to the point where the various advantages and disadvantages of using the various quote-unquote methods that I've spoken of become a bit more clear. Again, these aren't really huge things, but they're just things you should be aware of, ways that you can be limited or be forced to use other methods. So I'm just going to scroll through this first method, which is the mfile method, and then I'm going to talk about the other two methods. And the reason why I'm scrolling through the mfile method is that really, if I were to rename this function and then copy and paste it at the end of the function method, I would accomplish the same thing effectively. So I can just focus on the function method and the function handle method in that case. Now here is the function method. Again, we have normal things. Here are my initial conditions, my time span. I call ODE45 here. I do the plots here. Pretty much everything is done in the first part and in the primary function, except for the declaration of the function that returns the derivative of our state vector, s dot. That's declared as a separate function at the end, which we should all be familiar with by now. Notice that when I declare my initial conditions, you'll see that I have x theta v omega, not x v theta omega. When we're using this approach, we have to declare all the functions that we're solving for first for our state variables, and then our state variables include all the time derivative terms, or in this case, all the velocity terms. So it's not x dot, theta, theta dot. It's x theta, and then x dot, theta dot. Here's the time span that I've declared. Here's the numerical integration. I'm calling ODE45. Again, the results are x theta v omega, not x v theta omega. Okay, just remember that. Be very mindful of how your state variables are represented. when you're working with this matrix method as opposed to doing something by hand. And then I plot the results, right? So most of the work and challenge comes in making sure that your s dot function is made correctly. I have declared all the parameters already inside this function. Here are the parameters. Here's the forcing function. There's only one of them. Here's the mass matrix, damping matrix, and stiffness matrix according to what we declared or what we wrote out in the writing portion of the video. And then the zero and identity matrices are also declared. Remember that these are n by n matrices, where n is the number of equations that we have. We have two equations, so that gives us 2 by 2 matrices for both of these. Now, since these are square matrices, when I do this, I could just have a single 2 here, because MATLAB would assume a square matrix from that, but I included the 2 by 2 just to make the dimensions very clear. If you haven't guessed by now, the zeros function makes a zero matrix depending on the dimensions you specify, and the I function makes an identity matrix based on the dimensions you specify. After I've declared all these guys, you know, our mass and stiffness and damping matrices, our zero and identity matrices, then I can make A and B, which follow the equation that I showed in the writing portion of this video. You'll notice the absence of G and H. Again, remember that we don't have any gyroscopic or circulatory terms, so we don't have those matrices here. We just see K and C here. Here's B. And then here is our force vector, right? There was no force applied to the second equation, right? There was no force in the second equation, but there was a force in the first equation. That force is declared here as some general function, where this is some general variable that we can use. And now we're letting t be the variable that we're using when we call this force vector. And then here's a vector holding our vector of states, or I'm sorry, here's a vector holding our state variables. It is our vector of states, or our state vector. And then I declare s dot, just like we had in the equation in the video. S dot equals matrix A times our vector of states plus B times our forcing vector. Now, one thing I want to point out is that a faster way to do this is to negate this entirely. Just delete this line and then just write S1 through 4. And this makes a vector that has S1, S2, S3, S4. So this would be the vector of states. It's much faster, and it's especially faster if you have, like, say 40 equations. I won't want to write S1, 2, 3, 4 all the way to 40. It's much nicer and smaller and neater to write this. I just did this for the sake of, again, making it clear what we're working with. But you will see me use the shorter form in the function handle method because we really kind of don't have a choice. So here's the function handle method. It will be slightly different this time from the function method, and not just different in the fact that we can declare the function inside of this parent function here, this primary function, but different in other ways, and you'll see that in a bit. I have the same declarations. I still declare the mass matrix, stiffness, and damping matrices the same way. I still declare the zero and identity matrix in the same way, and I still declare A and B in the same way. But you'll notice a difference in how I've declared the force vector. And this is where we begin to see the kind of limitations of using the function handle method. When I was working with the function method, right, this function that I've declared here, or rather this vector I've declared here, is inside this general function, which includes inputs time and s for our time and our state variables, right, t and s. And I also have this function handle to give us a forcing function. So I was very easily able to do f of t here for the force vector because MATLAB knows what t is. It's an input into this function. The problem here is that if I were to remove this and do the same thing and just say f of t, There is no t declared. There's no t declared in this overall function. This function here does not have t as a possible input, and it should not have t as a possible input because that belongs to the function that we're using to return s dot, the derivative of our state vector. And because of that, since MATLAB has no clue what t is, MATLAB will return an error saying that t doesn't exist, right? It doesn't know what t is. You could think, well, maybe if I put it inside the function handle, it'll work. But the issue with function handles is that function handles are designed to take the inputs you specify, the general inputs you specify, and return one output, right? I mean, you could put a vector in here, in which case you could get a vector out depending on, how you declare the function handle. But in any case, it's returning one output, right? You can describe this guy so that it returns a single matrix, a single vector, a single scalar, but at the end of the day, it is supposed to return a single value if you input, two single inputs or however many single inputs that you have. All right? And so this doesn't really work here. What I need to do is make another function handle. And what this does is make a function that returns a vector that is the force vector. And this function is in turn calling another function that we declared earlier. And you can imagine that this will get a bit more detailed if we have multiple forcing functions that we're working with. I don't think it would get that much more complicated, but you really have to be even more careful with how you're declaring things. So we have to declare things this way because this is the only way that we can have this forcing vector declared without being given an error from MATLAB, and then allowing this guy to be fed to this declaration of our derivative of our vector of states. And also you'll see that here I use S1 through 4. I can't declare SVEC equals, S1, 2, 3, and so on for, again, the same reason. MATLAB does not know what S is yet. S is only a general kind of variable that MATLAB sees inside this function handle, and function handles are not used to make declarations or anything of that nature. Function handles are used to take the inputs you give it and return an output according to the input you give it. And just that, right? It's not like a physical coded function. And so that's the limitation there. You kind of have to jump through hoops to make things work in certain ways for the function handle method. And actually, you'll notice that you can actually be given problems where you're forced to only use the function method or the mfile method. So just be aware of that limitation. I like to use the function handle method when I'm dealing with a simple problem, and then I usually use the function method instead of the function handle method if the problem gets a little bit more complicated. In any case, once this is declared, and as long as it's declared without giving us an error, we can do what we usually do, declare the initial conditions appropriately, do the numerical integration, plot the results, and if I plot these results, I'll get what we've seen previously in MATLAB, the same results for x and theta, and if I plot the results using the function handle method, again, we will see the same exact results. So the results are good, the results are fine, they are the same, but just notice the limitations here, and that's really what I want to make sure you're aware of in this video. There are some ways in which the function handle method is limited, so if you like using that method, I strongly suggest getting used to one of the other methods. If you like this method because you can have everything ordered the way you want to and have everything in the same M file, then I'd suggest using the function method because it's pretty much the same except for the fact that the function that returns s dot is declared at the end as its own separate function. One thing that I want to point out though is that if you like using the mfile method, it's very powerful in this instance because all you would have to do is find a way, and I'm sure this is possible, all you'd have to do is find a way to pass the size, or rather the the number of equations that you have and your mass, stiffness, damping, and so on and so forth matrices to this function. And if you did that, then these declarations would kind of go away. You could still declare A and B and F in here, but other declarations would go away. But if you could find a way to pass all your matrices and vectors and such, and size and equation size specifications to this general function, then you can actually use the mfile method to solve any general problem that you have that is a linear multi-degree of freedom system. You can do it in the command window, you can do it in some mfile, but you could use it to pretty much tackle any linear MDOF system. Again, as long as you can pass the necessary matrices and variables so that the code runs appropriately. So that's nice, because it leaves you with the work of only really having to write the matrix or the matrices out and then passing them to the function. Technically, you only have to know the matrices for these other methods also, but you wouldn't be forced to rewrite these last few lines of code over and over and over again. You just have these once, and you could call them from anywhere for any linear MDOF system that you're working with. I still prefer the function and function handle methods, but those are just advantages that you can be aware of. Now, I just want to show clearly that the results are the same. You already saw the plots, but I want to show that if I were to plot what we got by hand, which is here, right? These are the state space equations, or the representation for the derivative of our state vector that we got by hand. And then this is the equation that we have using just matrices, right? Now, I want to show clearly that if I plot these results, that they will turn out the same. And I'm scrolling through the code so you can see it clearly. This time I'm going to plot all the results. So let's run this. And you'll see that I have the mass 1 displacement, mass 1 velocity, mass 2 angular displacement, mass 2 angular velocity, and of course, as expected, the results are the same. And why are they the same? Because the equations are the exact same, right? If you were to zoom in, you could see some small differences, and I'll explain that in a bit. So if I just keep zooming into this guy, for instance, and I zoom in some more, you won't see differences as quickly as you did when I showed the linear results versus the nonlinear results. But if you zoom in enough, and notice that this is a lot of zooming, whoops, that you will be able to see some differences. So notice these very small differences. I mean, just look at all these decimal places here, right? These differences are not very significant. And if you're wondering, does that mean, that the hand methods were different from the matrix methods? The answer is no. The reason for these differences is not in a difference in our equations. Both forms involve using linear MDOF equations, right? The issue is that when you're dealing with matrices, there are complications and tolerances and such when you're dealing with inverting and multiplying matrices and all the fun stuff that goes into there. And those complications aren't seen when we're doing stuff by hand, because we aren't dealing with matrices by hand. We're not like inverting matrices and doing all that kind of stuff. We're just taking the expressions directly and giving them straight to Matlab. Again, because that only those problems only come up with the complications of matrix multiplication and matrix inversion, you have to zoom really, 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 really deep to see a difference, because effectively there is no difference. This is a computer error, not a hand approximation error, right? When we did the nonlinear versus linear differences, you're able to see differences faster because there were clear differences. The two sets of equations that we used were different, and so the results were slightly different when we zoomed in enough. But for here, these differences are only due, again, to these complications with computers doing the multiplication and inversion of matrices. So now you've seen clearly that the hand results and the matrix results are indeed the same. And before I close, I want to make some quick comments in writing about the importance of all this stuff. I know this video is getting long, so you can leave here if you want to, but I want to make some quick comments. So let's go ahead and jump back to the writing. Alright, so we're back here for just some final comments. I really just wanted to make two final comments about using this matrix method with physical systems. And the first, which I've already kind of stressed, but I want to be clear, is that this method is very powerful and it's very useful, right? Because really, with this method, again, as I stated, as long as you can take your physical multi-degree of freedom system and get it into the matrix equation form after linearizing it, that is, as long as you can do that, then you can pretty much tackle any problem without having to do any work by hand, right? You won't see me writing out the gyroscopic and circulatory matrices here. But just know that if you do have those terms, that you can still use them as per the equation that we wrote earlier in the video. But I just want to write less because most often when people are starting out with this stuff, they don't really run into those terms. But in any case, if you have a physical system and you can linearize it, then as long as you can get it into this matrix format, you don't have to go through all the work that we went through earlier, right? I mean, when we were doing things with the linear system in the first video, which I believe was video 2B, we had to get theta double dot, and then we had to substitute that into the first equation, then get x double dot, substitute that back, and it gets really painful, you know. And if you don't linearize the problem, right, and you just have it as a nonlinear system, then like the work for that gets even more complicated, right? But it's already a drag to get things into state space representation by hand. And so this really provides a faster way. We can use matrix equations to get a straightforward expression for the derivative of our state vector. And though I wouldn't call it an automated method, which some would like to have, I can't provide that sadly, but I can say that this is, you know, either as close as we can get or close to as close as we can get. Because you don't have to do all the hand stuff. We just have to get the equations, which you'd have to do anyway. We have to know the forces, which you would have to know anyway. And then you just extract things into matrices. And then from there, you're just using matrix equations. You get the derivative of your state vector. You plug it into Matlab. So really nice, really easy way to derive stuff. And as long as you're sticking to linearized systems, you won't have to personally, physically derive by hand the state space representation for your physical system anymore. Another thing that I want to point out is that this is not just for physical systems. That was weird. This is not just for physical systems, right? You can use this with other problems as well. All you have to do is make sure that it follows the same general format. So let's say instead, you know, you're just given some math problem in some differential equations course, for instance, and they gave you x, y, and z to solve for, which sounds like a lot of work, right? But you had x, y, z terms, you had x dot, y dot, z dot terms, and you had x double dot, y double dot, and z double dot terms. Then you could actually extract a matrix, right? It wouldn't necessarily be a mass matrix, but you could extract a matrix that would multiply all the q double dot terms, right? Your vector q double dot. You could extract a matrix from that system of equations that would multiply the q dot terms, that would multiply all the velocity terms or the single derivative terms in your system of equations. You could extract a matrix that multiplies all the regular functions, the regular x, y, and z terms, right? You could extract all these matrices and multiply them by the appropriate vectors, or vector, and you could also take the right side of the equation, which would more than likely just be some kind of function of time, and then write those as some vector. And then from that point, you can again use the equations that we used earlier to then get the solutions for x, y, and z. So really this works for any system any situation where your system follows this kind of general format or can be put in this kind of general format. Really, your only limitation is that you have to make sure that you have a linear system or a system that you have linearized. And if you're going to linearize a system, make sure that you're justified in it, and you will want to show that your simulation of that result is accurate. All right, but that's all that there is to show. I hope that you can see the advantage of using this, and hopefully for those of you people who are working with really large problems where you have these however many equations and variables that you're trying to work with, that this matrix equation can really help you out in getting through things quicker so that you aren't breaking your hand trying to write everything out. So I hope all this information was helpful, and I hope that you're able to use MATLAB even more effectively now and more efficiently now than before. As always, good luck in your MATLAB ventures, and thank you for watching.